Okay, can you hear me? First of all, I would like to, of course, thank the organizers for organizing a fantastic conference and workshop here. It's a real pleasure. And I understand that everybody is already kind of a little bit worn down after this talk, so I try to be more brief. I don't know, and I can stop at any time, and we continue with questions because, like, basically, let me just give the punchline. First of all, so that you, like, if anybody like misses the line somewhere in the middle, then it's still like somehow sticks. That there are like there is this quantum toroidal algebra which looks super complicated, and there were lots of talks about it, and probably we're going to have another bunch of talks about it during the next days. Uh, but then, as sometimes happens in integrable systems, the algebra can be hard, but RTT relation presentation can be more or less tractable. So, and like the punchline is that it indeed is so. Like there are some explicit new formulas for R matrices for this algebra, which is super nice, and they make everything better. Like they have lots of applications to different different parts of this BPS algebra science. Like I'm going to list here not only formulas but also their applications, and this basically this part is kind of so going going to like cut it at some point, like stop it at some point to run over time. And the third part, to make the talk even lighter, is optional. So the third part is the application of this R matrix formulas to something very funny, which I like I haven't encountered in the integrable system business, but probably it should like also have a place in just spin chains and regular like all the conventional integrable system story where you in trace of some operator you take a spiral of this operator. So I'm going to explain what it means. Like when you take a trace, you usually draw something on a cylinder or on a circle, and then like connect the ends of the legs, outgoing and incoming legs of your operator or matrix or whatever, like R matrix. But in the spiraling operation, you instead don't connect the ends, but make them spiral around your cylinder. It turns out to be possible and meaningful. Again, so the punchline here is that this is an operation on R matrices, which has some very nice applications. Okay, so if you if you remember one thing from my talk, this is that the R matrices make everything better. So let me start with a very brief introduction because, well, I cannot give you a proper introduction because of lack of time, and also because many of you did a very nice job at introducing some of the quantum toroidal algebra I will need. So I'm going to work with the simplest quantum toroidal algebra of type GL1. So in principle, there are more. There are GLN/M, and there is a whole family of them. And Jean-Emile also like introduced a very nice generalization of GLN algebras, and I'm not going to talk about them. So I expect that something similar happens with them, but I don't have any results for them. So this quantum toroidal GL1 algebra, there is a bunch of ways to introduce it. Some of you are familiar with them, and let me just very briefly say, like, introduce it in a way I would, which would be easier to use in this second point. So I have the generators E and M, where N and M they live on a Z2 lattice. And there are also two central elements, say C1 and C2. Overall, the picture is SL to Z invariant. Well, with a you know, with a footnote. So in fact, one needs to consider the universal cover of SL to Z. If the central elements are non-trivial, this is the right group. So this is the group in which S to the fourth is not equal to 1, but instead it's some operation related to central charges C1 and C2. So this is the simplest way of understanding this algebra, but there is a definition which I'm not going to write, since I'm also not going to write out the commutation relations for E and M. Let me just write, so it is SL to Z covariant. And nonlinear invariant, nonlinear commutation relations. What is important for me is that there are three types of representations of this algebra. Three families. And they go by the name vector, Fock, and McMahon representations. So I'm going to focus on these two. The McMahon one I will not, I basically will not use, but the idea is that the states of these representations are labeled by one-dimensional Young diagrams, also known as integers. So the states here can be labeled as like this, or any other notation involving an integer n, you like. So in Fock representation, there are 2D Young diagrams. The states are labeled by 2D Young diagrams, which are the familiar pictures which I'm sure all of you have seen. So something like that, non-increasing sequence of integers, finite. And then in McMahon representation, there are 3D Young diagrams. That's the way the algebra is organized. I can give technical reasons for this, but the intuitive reason is that the algebra contains it contains two deformation parameters, Q and T inverse, but really, as I think Tomasz has emphasized, it really depends only on symmetric combinations of the following three parameters. These two and 1 over the product. So this three-dimensionality has something to do with these three parameters. There is a certain way of counting the states, like counting the characters of this state in a way. And it's not, yeah, which is related to these three parameters. So this 3D space has something to do with every axis being counted with the corresponding parameter. And I'm not going to explain this, but like, if you, I can give more details after the talk. So that is the mnemonic. So here you have to, and perhaps it's important to emphasize that here the same mnemonic works. Like this axis in the plane, they are also labeled with a pair of deformation parameters. So you can write here Q and T inverse, or vice versa. It will correspond to the transposition of lambda, so it will be a rewriting of basis, just a change of basis in your representation. But if you choose a different pair, Q and T inverse, instead, if you choose Q and T over Q, this will be a different representation. It's isomorphic, but different. So if you consider, you can consider various tensor products of various representations like this. So if I have here Q and T inverse, I will label this representation F Q T inverse. Okay. So here with vector representations, it is quite similar. So I should look at my integers just as like one-dimensional Young diagrams, something like this. So this is my n. Well, n can be negative too, so it's you need a little bit of imagination to imagine it's a Young diagram. But here is this Q is one direction which I choose out of three in which my diagram is going to grow. So here in the 3D case, it will grow in all three directions. For example, there is a diagram with a single box here. So this I will call this vector representation I will label by VQ. So this Q indicates the direction in which the diagram grows. And there are again three choices which are isomorphic but different. Okay, so there is one more label of a representation, a Fock representation. So let me forget for the moment about the McMahon representation because I'm really not going to use it. Let me instead write out another label. So another label of the Fock representation is the central charge. So the central charge of a Fock representation is non-trivial. So for this V, in this V representation, C1 is equal to C2 is equal to 0. In the Fock representation, one of the central charges is 1. The second is 0. But you can choose, because if you have a SL to Z covariance of everything, like if you have a representation like this, you also have a representation in which you act with any element of SL to Z before acting in your representation. So C1 and C2, they transform as a doublet under this SL to Z. So you have to indicate which choice of this direction in the plane you have for your Fock representation. So I will indicate here my choice on top. So this is going to be my labeling of the representation, of the Fock representation. So in principle, there exists an infinite number of these Fock representations which correspond to the SL to Z orbit of this 1, 0 vector. Yes? GL1 with less heads is just, well, you have this remains the same. So what GL1 with one head is just going to be, okay, let me move it back. It's just going to be Heisenberg algebra. So Heisenberg algebra acts on it has a highest weight representation. So you have Heisenberg algebra, which is GL1 one head. It has a Fock representation, just its highest weight representation. States are labeled by lambda diagram. And for this VQ, the situation is more or less trivial. You are just going to multiply by a single variable x or something. You can view it as a representation of the algebra of polynomials in one variable. It's commutative. Yeah, but GL1 is subalgebra, so if you have a representation like this, you also have a representation for one head. Yeah, so maybe you're asking if it is still irreducible. So like you have a representation of a if it is a representation of a bigger algebra, it's still a representation of a subalgebra, right? So because like one head is a subalgebra of that. So it's still a representation, and it turns out that this concrete one is still irreducible. So yeah. 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 Doesn't act, sorry? It's a simultaneously on N and M and C1 and C2. So you'll have to, I'm sorry, I missed that point. Thank you very much. So SL to Z acts on N and M as a doublet and on C1 and C2 also as a doublet. So that's the key point. Now let me introduce, so I didn't write commutation relations of the algebra, but I am going to write at least one explicit formula for the generators in the vector representation. So in the vector representation VQ, suppose we have chosen Q, and there I can understand my representation as follows, as a representation of difference operators in a single variable x. So I write E and M, let rho be my representation. So it sends a generator of my algebra to some irrelevant constant, explicit constant, which we know, times x power n q minus m d by dx. So what is this? This is a difference operator which acts on functions. Yeah. Yeah. There's an infinite number. Yeah. Mm-hmm. I can tell you for, well, different things happen for different slopes. It depends on the slope. So for one slope, what happens is what I've just told you. It's going to be a representation of a Heisenberg algebra. For a perpendicular slope, like it's going to be Heisenberg algebra with sort of zero central charge. So it's going to be commutative algebra in an infinite number of variables, and this will give you act with certain numbers, just with powers of the spectral parameter, basically. So it will be a stupid action. Something in between, it will be still some action like this. Just I cannot tell you right away what it's going to be, but it will be some simple modification of that. So indeed, it's a good question, but so no magic happens. So this is a shift operator which just multiplies x by q power minus m. So this is a multiplication by x and the difference operator in x. So you see here SL to Z invariance, it will exchange x operator, which is the multiplication by x, and a p operator, which is the difference operator. So we immediately see that px is equal to q inverse xp. And this is the relations of the quantum torus, hence the name quantum toroidal algebra. And of course, SL to Z x. Here the central charges are trivial, so there is no funny business with the universal cover. Okay, so here is the explicit formula. Now, the next point I'm going to emphasize is that the algebra, it's a Hopf algebra, quasi-triangular Hopf algebra. So it has an R matrix. So has an R, a universal R matrix. And as for many algebras, there is a formula for the universal R matrix of the type of the type discovered by Kharoshkin and Tolstoy, which is basically the product over slopes in Z2. So let me label my slope by S, and this is an ordered product over all positive slopes in Z2, and there will be RS, which itself is an exponent of the form like this. So a slope is a vector. Is a vector in a Z2 lattice. So what this formula tells us is that we have to take the product over all rational slopes in certain order, like this. And then for every slope, I should evaluate this infinite sum of generators. So here, S is a rational number, and N is going to be, well, okay, so S vector is S1, S2, coprime. Yeah. I'm not prepared to speak about Yangians in this, I don't know. The original Kharoshkin-Tolstoy formula is valid for Yangians. So, but with a Yangian, I'm not sure. What I wanted to emphasize is not to frighten you, or maybe to frighten you with this formula. Well, these are some explicit coefficients, but the sum is infinite. So the sum over all generators lying on this rational slope, rational array here, and then there is an infinite product. So this is a very cumbersome formula. It's well, yes, I think it's a theorem. It's a theorem by Fagin, Jimbo, and somebody. And I'm not exactly sure if it is proven by Fagin or by Negots, but some combination of two definitely proved it. Yes, yes, and we of people. Explicit formula, explicit case, explicit product. Everything is explicit. I guess it's Negots. So, but it's a theorem. It's not like a guess or conjecture. The problem is that the expression is very complicated, and Negots has some way of working with this subalgebras and proving this type of formulas, and some of them are very complicated. What I want is to Dreamfield double construction. Yes, yes, I guess so. Yeah, yeah. I mean, okay. He has different formulas. This formula is definitely proven. What I want to say is I don't want a complicated formula. I want a simple formula. So, yeah, sure. Universal matrix is an element of. Let me call this A, and this belongs to A tensor A. And I probably need to put some head here because it's an infinite sum, but infinite linear combination. But what is important is that an element of an algebra tensor algebra. So it is not evaluated yet in any representation. So it's valid for any pair of representations. That's why it is universal. Yeah. Absolutely. For any pair of representations, modulo some complications about convergence, which I don't want to emphasize. Yeah. Well, yes, that's probably the reason, but I don't know an explicit way of going from one to another. I agree that the form is very suggestive with product over slopes, etc., etc. I know another formula, we can discuss after the talk. I know another formula which is exactly corresponds to the simplest wall crossing formula for certain elements of this huge algebra, like the pentagon relation for the elements of this algebra. But that's different. Yes, yes. I agree that that might be another way to. That is probably another proof of the formula. Yes. Okay. Sorry. So yes. Sorry. Yes. How does it act? It acts with if I have a power of x and power of p, this is L to z acts on n and m. So n m is acted upon as a doublet again by this as L to z, like this. So S exchanges x and p. That's the idea. So I want to evaluate this R matrix. And there are some papers by Neguts and others where they evaluate this R matrix for certain pairs of Fock spaces. And the formulas are still quite complicated, though a bit better than this infinite product. They're still infinite sums. So what I want to start with is, yeah, sorry? Yeah, you absolutely will. Because you have a non-trivial product in this algebra. So you have it's a Hopf algebra with a non-trivial product. So if you act on well, it gives you a McDonald polynomial in one variable. If you want more than one variable, then you take a coproduct. And the coproduct is going to be non-trivial. So delta of E and M is going to be something non-trivial. So it's E and M tensor 1 plus horrible. So this horrible part, if you evaluate them it in this simple representation, the horribility like cancels, like compensates by the simplicity of the representation. You are getting precisely Macdonald operator. That's it. So because this representation is very simple, the naive idea is to evaluate the R matrix in this representation, this vector representation times something. And this is the first thing I'm going to introduce. Okay. So explicit for now we come to explicit formulas for R in representations. New explicit formulas. So the first one is the simplest one again. So this is the one of the main results. So I can take a tensor of Fock and vector. So Fock is going to be 1, 0. And now I have a choice. I basically have to choose labels here. And there are two essentially different cases. The first one is going to be if I choose some pair of parameters. Choose the third one here. Yes. Well, vector tensor vector is too simple. I don't know. Like well, okay. The technical thing which because why I don't want to talk too much about vector tensor vector. Vector is not a highest weight representation. So there may be a problem with defining this thing there. So I'm not that confident about the tensor product of vector tensor vector, though I have a formula for that. I just don't, I'm not prepared to give it out as a theorem, while for this one I am. So the first choice is that when this parameter is distinct from these two, there is a choice like that. And then the R matrix in this representation this is probably the only explicit formula I'm going to write, but it's super nice, and you see it's not horrible at all. So I have a V plus and V minus, which are vertex operators. And I have U, so I'm going to explain the notation right now. So what we have here, so U is the spectral parameter associated to this Fock representation. So Fock representation contains an additional parameter, like it's like a dimension or momentum of your free field. So this is U, this U enters here and here. And V plus and V minus are vertex operators. So free field vertex operators, like this. Yeah? Yes, yes. So this is precisely what gives you Q Muir transformations, and what is giving you out the W algebras. But you can, yeah. The short answer is yes. So this is the same thing. So here are the free field, some free field vertex operators. It's super simple. And what can you do with this operator? Like you can, well, you can, an R matrix, you can stack them together. That's basically the one of the ideas in the integrable systems. So you can do the following. Let me draw it like this. Sorry. So what I want to say is that one can prove explicitly that this satisfies the R matrix relations. It determines it uniquely. So this is an R matrix of the quantum toroidal algebra, really. This one, ANs. There are ANs which are the operators, the free field operators. So AN, AM, they satisfy the commutation relations like this. Well, this is just a factor, but what is essential here is this field vertex operators. So you can draw it like this, where this dashed line represents a vector operator, a vector and this F gives you a Fock representation, okay? So this is a way to picture it. And then it turns out that this, yes? Sorry? Which one? Everything is already taken into account here. Of course, even in two ways, actually. Okay, for the specialists, like let me. So you have, of course, you can do, and this way you make actually make contact with some operators, some cumular operators. That's how you do it. So you can write this out in two different ways. Like you can factor out v minus. So v minus only contains negative modes, so it's an exponent of negative modes. So it's invertible kind of. So you can factor out just this part completely, and you say, let me write it out schematically, that you have one plus, and here you will have q over t u times v minus inverse v plus times t over q x dx. So what we have here, this is going to be the Cartan part, R0. So this belongs to the Cartan. Just the thing is that I evaluated in a tensor product where one part of the Cartan, it gives me this A operators, and the other part gives me the X multiplication by X. Recall that that was the question, like how do I act if I consider on a subalgebra, GL1 hat subalgebra? That's exactly what is contained in this R0 piece, which is essentially this one. This one. This is even more Cartan part, because actually the formula for R matrix, here it contains, of course, I skipped a little bit. So you have here a prefactor, which is like exponent of C1 times D1 plus, well, D1, okay, times C1. Sorry, let me write it in this Einstein notation, right? Sum from 1 to 2, Ci di, di Ci. So Ci are the central charges, and Di are the grading. So if you write it out like this, you get exactly this part, because one of the central charges is non-trivial. It's more or less q over t, logarithm of q. This the problem is that you cannot, like, a vector representation. It's an evaluation representation. So in evaluation representation, as in a fine the algebras, you know, the grading operator doesn't really act inside the representation. The grading operator shifts the spectral parameter of your evaluation representation, right? So that's what D does in a vector representation. So that's the explanation of why this thing appears. So x d by dx really shifts the spectral parameter, like the spectral parameter of this VQ, which is really, it's in a kind of an evaluation representation, if you wish. Okay, I guess we can discuss after the talk, or if yes. Extend with you mean I can write something instead of this x d by dx here, and this is going to be some other algebra or something else? Okay. Ah, okay, I guess probably I can do it, but just this formula turns out to really satisfy the intertwining condition of an R matrix. That's what I want to say. So Perhaps you can consider a larger. Should I continue? So this is the factorization. So this is the R0 part, and then there is 1 plus, in principle, an infinite sum. But in this case, the infinite sum truncates to the first term, and there is only the first term here. And this is the what is called the Q-Miura operator. And you can read about it in the work of Harada, Matsuo, and a couple other people, which I unfortunately don't remember. I'm sorry. So these are Q-Miura operators, and what the job is that, like, now it's a nice expression, but what can you do it? Applications. Applications of this nice R matrix. What can you do? You can stack this R matrices either vertically or horizontally, and both are fruitful. So the first let us consider the vertical stacking, like this. If I have 2 of them, so the R matrix contains 2 terms, V plus and V minus. So I can write here an index plus or minus on every crossing. And this will give me different powers of the shift plus or minus powers of the shift operator. So if I consider something like this, is going to be an operator acting on a tensor product of 2 Fock spaces. So it's going to be an element of a pair of Heisenberg algebras, a product of 2 Heisenberg algebras. Now, if I expand this out in this shift operator, this is going to be a sum of certain operators, wk of x. So I have my x variable sitting here on this line. So this is going to be wkx times t over q k x dx. So I expanded powers of the shift operator, and also in powers of this u. This is the same as you can see here. So u appears always together with this d over dq, and I have this R0 prefactor in front, which I'm not going to need. I'm not going to talk about it. It's not going to play a role. Again, I can explain why, but just let us skip it for the moment. If I have 2 of them, there is going to be just the second power. But if I have n of these Fock spaces, it's going to be nth power. So these wkx are very special operators, which were again discovered by Harada, Matsuo, and other people. They are obtained basically from the product of these brackets. If I take a product of these brackets, I get the generators of a W algebra. Now, why? Well, W algebra, so let me emphasize. So this is the generators generating currents of QW algebra of GLN. GLN type QW algebra. Now, as you can see here, the situation is a little bit tricky. If I take a product of, so this gives me a product of my R matrices. So this is going to be R times R times R n times. And when I factor out this piece, it is not going to commute with the other R's. There is going to be some modification in these brackets when I commute stuff around. But all this boils down to what Harada and Matsuo did. Just it's a very streamlined version way of obtaining their formulas. So I get the same generators of QW-GLN. Now I can explain why you get QW-GLN. Because QW of GLN is well, there are many definitions, but by the most common definition is an algebra commuting with a set of screening charges. So the subalgebra of n copies of the Heisenberg algebra, of a free field algebra, commuting with a set of screening charges. Well, the screening charges, they have explicit form, and again, it's without knowing the overall quantum toroidal structure, this look like some ad hoc construction, but the screening charges turn out also to have meaning, and they have the following meaning. Like if I have a pair of Fock spaces, I can consider an intertwining operator like that, where here runs, sorry, doesn't matter in which way to draw this, but let me just draw them in the same way as here. Here runs the so this is the screening charge Q. And this automatically commutes all these generators obtained from the R matrix automatically commute with this, because what are these dots? So these dots here are intertwining operators of the big algebra A. Since they're intertwining operators, they automatically commute with this pair of R matrices. If I put my screening charge here, I can pass it through without any problems, and I have a system of screening charges sitting here, there, everywhere. So this is a nice way of obtaining QW and algebras, and in a similar way with a little bit more sweat. So this I'm not going to explain. You can consider F Qt inverse tensor VQ, where this is one of the parameters in the representation. And from this you get a more fancy R matrix, which is now an infinite sum. So this is going to be an infinite sum of vertex operators, but still tractable. So there's a bunch of vertex operators, and then you can obtain, so let me not pause too much on this, but you can obtain GLN/M or a general corner vertex algebra, which basically Harada Matsuo tried to do, and they obtained some simple examples. But with this formalism, you get the general answer immediately that you know that this is a W algebra commuting with a set of screenings, and everything works because of the R matrix relations. Okay, now let me, I still have a little bit of time. Uh-huh. Okay, did I understand correctly that you say that there is a way to explicitly solve for this vertex operators here from the recursion relations of for QQ characters, basically? No. Uh huh. Uh huh. Okay. Okay. Ah. Okay. Uh huh. Okay. Ah. Okay. 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 So, yes, sure. In this way, you can also obtain this. I'm sure I just didn't do it that way. So I just solved the commutation, like the intertwining relations, but that should give the same answer. And yeah, No, it's going to analog. Again, the formula for that was it's like Q per hammer symbol. Okay. Sorry, if I start with our matrix and yeah, yeah. Why? Because it commutes with a set of screening charges. Yeah, yeah. You can just do the do the same thing, like take an element, a particular element of this quantum toroidal algebra, evaluate it in the tensor product of Fock representations, and this again is going to be to automatically commute with this Q because this Q is an intertwining operator basically, and this will show you that this the action of the algebra on this particular tensor product of Fock modules gives you it truncates to a QW algebra. Yeah, you need to know something to define. Like you need to start with something. It's just you need to either start with screen charges and say that this is my Q deformation of screen charges of the standard W algebra, or you need to start with quantum toroidal algebra. You need to start with something. This one, why it corresponds to the screening of the. I don't know where do the screening charges for QW algebra come from originally. I think they were defined by Frankel and Reshetikhin sometime in the end of 90s. Not immediately, not immediately. Is there a moderator? Okay, sorry. So now the question is like yeah, you want a spiral. Let me bring so just a short remark on this, that you can also stack horizontally. So you have application say 1, application 2 is there was a talk by Yehao about calogera systems. If you want to do a Q deformation of that, you can just stack these R matrices horizontally and then plug in the vacuum stays here. It's going to be an operator, a difference operator in x1, x2, etc. Difference operator in x1, xn, and a very particular one, which is actually equal to the sum of trigonometric Rujinars-Schneider Hamiltonians from 0 to n. There is going to be, of course, all these powers of u, and these are kth Hamiltonian of trigonometric RS integrable system, which is very nice. You have a universal like a universal formula for this Hamiltonians just from commuting this V plus and V minus. Now the spirals. Okay, let me in the remaining minute just draw some spirals for you. Like, what is the idea? If you want, you can take a compactification of these nice pictures and see what happens. Well, then the question is, of course, what do you want to obtain? You can take just a trace, so spirals. You can take a trace of this. For example, if you have a single R matrix and you identify this state with that state and sum over, well, you can do that, but this just gives you one term of this R matrix, V minus, depending on your, like, you actually need to shift your parameters here. You need to introduce here a small box in which sits the shift operator, mu to the d1 and lambda to d2, where d1 and d2 are your shift operators. So this is the most general type of a trace. So you take a, this is corresponds to a trace over v mu times d1, lambda times d2 times your R matrix. Trace over the first, like over the first leg, okay? Oh, sorry, the second leg. But this turns out to just give me one of these terms depending on my mu. So if mu is square root of t over q or q over t, this gives me one of them. This is kind of boring, well, it gives you a bunch of commuting operators, which are this a_n's for positive n, and they trivially commute because they are creation operators. Okay, so the non-trivial thing which you can do is to adjust this mu so that the representation which comes out of here does not match the representation, the spectral parameter here and there, they don't actually match. Now what happens then? Then happens the spiral. So if you try to imagine a cylinder here, so these two sides are identified but with a shift. So these two parts identified but with a shift. So this representation, it goes out here. So this is identified with that instead. And this part is going to be identified with the next one, and so continues. So this continues for an infinite number of times. And at every crossing, you can put a plus or minus, a plus or minus, a plus or minus, etc. Now, well, one can think what it resembles, what it looks like, but one can just evaluate this, and it turns out that this is equal. This is going to be an operator acting on the Fock space, right? And this operator, the sum here is over plus and minuses. So I can recall that this bunch of pluses and minuses is really a fermionic state. You can think about it as a fermionic state. So sum over Maya diagrams. What's a Maya diagram? A Maya diagram is precisely what happens here. It's a bunch of pluses and a bunch of minuses sitting at integer points. So this is going to be a vacuum state, plus, 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 then minus, minus, minus at some point. So there is a sum of these Maya diagrams, and for every Maya diagram, you get a certain vertex operator, okay? Let me denote my Maya diagram by M. Yeah, I fix an asymptotic so that it is plus here and minus there, and that's my definition. But then what is important is that, first of all, so this sum is a product of my R matrices, an infinite product of my R matrices taken along this Fock representation. So it factorizes. It's a factorized product of vertex operators. But on the other hand, it's a sum of, I can rewrite a sum over Maya diagrams in a standard way from the theory of fermions, that you sum over the vacua. So there's the place where pluses change into minuses. I can shift it. So I sum over this shift, which I denote by k here. What remains if I fix the vacuum, if I fix sort of the overall number of pluses minus minuses, so it is like that, I can still exchange minuses and pluses like that. And this gives rise to a sum over Young diagrams. So lambda here is a Young diagram. So in the end here I have a second expression, which I denote by chi lambda. And this turns out to be an affine QQ character. Or affine W algebra generator. This is the, turns out to be a very nice expression that if you, and here you have a sum over shifts by mu to the power of k. It is factorized, it is the sum of Maya diagrams, and there are these three equalities which are very, very nice, I think, that some version or some limit of it has been obtained by Nekrasov and Andrei Grekov. But here it follows automatically from this R presentation that this is going to be a generator of affine W algebra. This, if you circle over the cylinder, it gives you an affinization of this. Sorry, I've run out of time. I beg your pardon. Thank you very much. If you have any questions, you're welcome. Yes, with pleasure. So all this story about classification of representations and pictures, drawing pictures, the pictures look a little bit like brain diagrams, and this is not a coincidence because the idea and the intuition, the physics part, is that this algebra, it really describes states like, let me try to make a correct statement. The representations of this algebra correspond to branes of type 2B string theory. So this classification with McMahon, with 3D Young diagrams, so these are going to be branes of type 2B string theory. So these are PQ 5 branes and 7 branes. So they're also like PQ 7 branes. So this P and Q, very opportunate, they correspond to the central charges. So they are going to be P and Q here. And this D3, you know, it's invariant under SL. So SL2Z is going to be SL2Z as duality. So this is going to be as duality of type 2B. Now, we know that D3 brane is invariant under S duality, under the whole SL2Z. So hence it is, the central charges are 0, and it really is invariant. So I can cook up an operator which just transforms my generators in this representation, and that's it. Well, these guys, they transform into each other because this C1 and C2, they are doublet under SL2Z. So P and Q transform as they should under S duality. Okay. Now the 7 branes is more complicated story, but in principle, like this is the idea. So this describes some. Okay, the intuition is that there's a bound state of 1 branes with this brane. So I don't want to talk about D3 because this is shaky, but for 5 branes, the bound state is basically a bunch of instantons. So my operators, they add or remove boxes of lambda, hence add or remove instantons on the world volume theory of a bunch of my 5 branes. So this is what happens. And for 7 branes, it's like the kind of 3-dimensional, like kind of instantons on C3. These are going to be enumerated by 3D Young diagrams. Yeah. Because I also have some. I have a picture in which my brain propagates. So one direction is here, and there are like the instantons are not going to. They are going to expand this direction. So there is not. This direction is not the one. Okay, let me just write out the directions in which all these things live, just to make it a little bit, perhaps a little bit more understandable. I have a Amiga background like this. So I have C3. I have an X direction, Y direction, say tau direction, and an extra circle S1. So if I have a 5 brane corresponding to F Qt inverse, say 1, 0, okay? Now, this is going to span one complex direction, hence 2 real directions here, 2 real directions here. It is going to span this X as in the picture. This is my X. And all the branes I'm considering are going to span S1, 2. So what happens, like this story with instanton happens only on this part of the geometry. So that's the explanation, and that's why this Q and T parameters are the equivalent parameters counting these boxes of lambda. Yeah. Yeah, so this is X, this is supposed to be X, and here this is supposed to be tau. And X and Y. Y is not visible, Y is somewhere, so this is not everything can be drawn on a single picture. But basically the idea is like that. So on R, X, and Y, this is where SL to Z happens. And hence, if I compactify, I consider compactify branes. And then, so this dashed line is supposed to be D3. Which one? It is, because for reasons of supersymmetry, you need to, if you consider brane setup like here, which I unfortunately I haven't written out completely, but if you want to conserve supersymmetry, you need to rotate simultaneously your your PQ charges and the orientation of your brane in X and Y, so they are tied together. This is like an Witten setup. This is the same thing, that the orientation of the D5 branes and then S5. Sorry? Yeah, right. Okay, I don't have to rotate the branes, but I have to get an equivalence. I need to consider. To consider, like, to change the branes. That's what I say. This guy who is spiraling here is a D3. Not always. You can consider D5 too. It's spiraling. You can consider a different slope, but you can consider vertical slope, and that is also going to be all right. Sure. Yeah. Yeah. I cannot exclude it, though I doubt it. And I don't have a definite answer. Not really, no. In this construction, no. Well, there is a story about SL to Z, but not in this construction of our matrices. So I didn't do any duality really here. I evaluated everything in a fixed duality frame, sort of.